Now that we've gone through all of the reactions of the TCA cycle, we need to take a look at overall what we've done. So between glycolysis and the TCA cycle, we get a lot of different things. So from just the TCA cycle, we get 3 NADH, 1 FADH2, and 1 ATP are generated. So granted, it did take that acetyl-CoA and a lot of different cofactors to do that, but you do get that. You notice that you also are going to get this relief of 2 carbon dioxide units. So this is going to basically waste or get rid of 2 carbons through carbon dioxide. When we then go ahead and add the oxidation of glucose by glycolysis, then not only are we using glucose in there, but then we're also yielding more NADH as well as more ATP. The reason why you see fairly drastically different numbers is, remember that when we're looking at acetyl-CoA in the TCA cycle, that 1 acetyl-CoA unit comes from 1 unit of pyruvate. When we're now talking about glucose going through everything, remember we split glucose in that second phase of glycolysis, which means every glucose molecule would produce 2 units of pyruvate, which then is going to give us 2 rounds of acetyl-CoA. So that second box has a lot more stuff in it because a lot of the things are then doubled. So that's why you've got those 2 rounds of FADH2. Those amounts of reducing power from that 10 NADH and those 2 FADH2 is going to make a lot of molecules of ATP in electron transport and oxidative phosphorylation processes, which is coming up so very soon. So the TCA cycle has both catabolic and anabolic pathways in it. So the reason why I love this picture, which I know is a little bit small, is that it does a good job of showing how things are interrelated. So before we take a look at that dynamic map of metabolic pathways and how different things are connected. And your TCA cycle is exceptionally well interconnected to both catabolic and anabolic pathways. So just looking at this, you can see both amino acids, you can see both making purine nucleotides and pyrimidine nucleotides. You've got some porphyrins going on. There's all kinds of different things that can be made, steroids and fatty acids from acetyl-CoA, lots of different stuff that comes in and out of this pathway. We call these anaplerotic reactions. So anaplerotic means filling up. And this is to help prevent the TCA cycle intermediates from becoming depleted. So we need ways that if we're going to take things out of the TCA cycle, that we can feed things back into it. In order to do this, we're often going to use carbon dioxide to feed back into the TCA cycle. So one thing that we can do that's really that helps a lot with all of this is to take pyruvate, and by using pyruvate carboxylase, we can make oxaloacetate. That pyruvate carboxylase to oxaloacetate and that use of that 1 carbon dioxide unit hopefully sounds familiar because that's also found in gluconeogenesis. So before, when we were talking about gluconeogenesis and that role in the mitochondria and that formation of oxaloacetate, that's also helpful here and is the exact same enzyme having the exact same reaction that we see in gluconeogenesis. But instead of going on to make a molecule of glucose, it could go back into the TCA cycle. You'll notice that there are other options here besides the pyruvate carboxylase. You can also take pyruvate and then using a malic enzyme make L-malate instead, which can also then be used to go back to oxaloacetate. That does involve more cofactors and more steps in order to make that happen, but again, is possible. You can also take phosphoenol pyruvate from glycolysis and phosphoenol pyruvate carboxylase to make oxaloacetate. So there are multiple options here, but we're going to take a little bit more time to talk about the pyruvate carboxylase. So in animals, that pyruvate carboxylase is the most important one because it does provide that direct link between glycolysis and the TCA cycle. That enzyme is going to be activated by CoA. So essentially, when you have more CoA than you have oxaloacetate, that pyruvate carboxylase is going to be stimulated to make more oxaloacetate. So essentially, the cell's kind of geared to have equal amounts of oxaloacetate and acetyl-CoA. And when that fails and you have more oxaloacetate than acetyl-CoA, that pyruvate carboxylase kind of gets into gear to keep those ratios similar. Now it's time to talk about regulation. So we're going to talk about regulation actually in 4 places. So 3 of those are in the TCA cycle themselves, as well as then pyruvate dehydrogenase. So we're going to talk about it in forms of citrate synthase, isocitrate dehydrogenase, alpha-ketoglutarate dehydrogenase, and then the pyruvate dehydrogenase. You can see all of those here in the diagram. Now what we're actually going to do is, since those are all regulated by similar molecules, instead of looking at these enzyme by enzyme, we're going to take a look at how they're regulated by the different factors. So we're going to start with NADH as well as NAD+. So in here, NAD+ is going to activate the cycle. So high NAD+ is actually a signal of low energy status. Remember, we're going to be able to use NADH, the reduced form, in the electron transport chain. So the more NAD+ we have, the more that signals that we've used our NADH. So NAD+ is going to activate pyruvate dehydrogenase. NADH is going to inactivate all of our enzymes. It's going to inactivate pyruvate dehydrogenase, citrate synthase, isocitrate dehydrogenase, and alpha-ketoglutarate dehydrogenase. ATP, another high energy signal, will also inhibit the cycle. So ATP is going to inhibit pyruvate dehydrogenase, citrate synthase, and isocitrate dehydrogenase. Low energy signals, AMP and ADP, will activate the cycle. ADP will activate isocitrate dehydrogenase. AMP will activate alpha-ketoglutarate dehydrogenase. So as you look at these, realize that those are all affecting the 4 different enzymes we've been talking about, but some of them are affected by ATP, some of them are affected by ADP, some of them are affected by AMP, and isocitrate dehydrogenase is affected by both. Succinyl-CoA is going to also do some inhibition. This is going to act as a signal that the cycle is saturated. So this is going to do that feedback inhibition loop to basically say, hey, we have enough stuff. So succinyl-CoA is going to inhibit citrate synthase as well as alpha-ketoglutarate dehydrogenase. Note that those are specifically inhibiting the TCA cycle. They actually leave the pyruvate dehydrogenase alone. So those are a feedback inhibition loop, but just for the actual cycle part, and they don't affect pyruvate dehydrogenase. Taking a closer look at pyruvate dehydrogenase regulation, what we can see here is that whenever we have acetyl-CoA and NADH, so the acetyl-CoA being the product and NADH being that high energy molecule, both of those are actually called allosteric inhibition. So even though your acetyl-CoA fits in the active site because it is that product, it actually is going to affect it allosterically. So it's going to bind to the enzyme in another place. This also has another form of regulation, though. It is also covalently, this also has covalent modification for regulation to a serine residue. That will inactivate the E1 portion of the dehydrogenate complex. There's a pyruvate dehydrogenase kinase, which is activated by NADH and acetyl-CoA. So NADH and acetyl-CoA will activate a kinase to add another layer of regulation on top of this. So once NADH and acetyl-CoA activate the kinase, that will then phosphorylate the E1 portion of the pyruvate dehydrogenase complex, which inactivates the pyruvate dehydrogenase complex.